Alright, so what I want to get into now is a little bit more of the regulation of this filtration and kind of the factors that influence it. One of the things a lot of times is that when they start talking about urine formation, that one of the things they talk about is glomerular filtration rate, which is basically how much filtration are you making in a certain period of, how much filtrate are you making in a certain period of time. We're going to see that it's a combination of a number of different factors, and some of this stuff that we're going to talk about here is a little counterintuitive. But really what it kind of gets down to is you have pressures and factors that are going to favor filtration being formed, and those that are going to work against it. We're going to see kidneys are highly involved in blood pressure regulation to try to keep this conditions that make it efficient for it to make its filtrate. So these ones should seem familiar. This is stuff we talked about with blood pressure, and we talked about capillary exchange of water. But again, you have a net filtration pressure. This is going to be that blood pressure or hydrostatic pressure in the glomerulus, pushing those fluids out. And then again, against that, we're going to have any back pressure of the fluid in the tubules that could be pushing against that. So let's say you somehow had, usually it's close to zero, but if you had some type of blockage that was causing back pressure, that might stop your ability to filter. The other thing that is working against this is the osmotic pressure of the blood, which again is the fact that there's those albumins and other stuff that are in there. So overall, the forces that are favoring stuff going out is this net filtration pressure. Again, glomerular hydrostatic pressure is going to be also the fact that there is some dissolved substances in the glomerulus that could also draw some more of this here. Glomerular hydrostatic pressure. Sorry, I said the wrong thing. That is that blood pressure that's present in there. And again, that's what's pushing this out. Again, without this, we don't have a filtrate. We're not going to form urine. If you don't make it filtrate at all, you don't have urine. We're going to see there is some interesting stuff that goes on with this. We have that afferent and efferent arterial. So the afferent bringing blood into that glomerulus where the slits and the filtration membrane is, and the efferent taking stuff out. We're going to see that there's differences in the diameters of those blood vessels, and we can do things with that to kind of favor this filtration to happen. But generally what we see, bigger diameter in the blood vessel taking blood into the glomerulus, and a smaller one on the exit. What that means is you're going to build up pressure in the glomerulus where we want the filtration to take place. Again, as what I got ahead of myself, the blood colloid osmotic pressure is what's working against us. Those plasma proteins, that is going to try to draw some fluid back into the bloodstream. At least in the kidneys, this is going to be minimal. It has a role, but generally not as much a role as what we'll see in normal capillary beds. You can also have this capsular hydrostatic pressure. That is that any buildup of fluid in the tubule system could create a back pressure, possibly. Normally, this should be closer to zero, though. Not zero, but closer to it. So determining net filtration pressure, you can kind of see here, if pressures promoting filtration are greater than those opposing, we're going to make a filtrate. So if we have 60 millimeters of mercury hydrostatic pressure, we have the osmotic pressure against it, as well as any hydrostatic pressure of the tubules. Those are all things that would work against it. But if this is 40, this is 50, 60 minus 50 is going to be 10 millimeters of mercury net filtration pressure. So again, that glomerular filtration rate is the rate at which you're producing this. If you get increased filtration pressure, you're going to get an increased filtration rate. So if that net pressure is not 10 and it's 20, you're going to make more filtrate in a shorter period of time. And again, increases the GFR, like I said, there increases the solutes and water remaining in the tubular fluid, increases substances in the urine, decreases urine filtrate reabsorption. The main thing on any of this is that you have to realize is that I always use the analogy. It's an old school, really old school show before my time. But if you've ever seen the I Love Lucy, where they have the chocolates on the little conveyor belt. If you're putting chocolates into a box, if the conveyor belt's going at a certain speed, you're going to do it perfectly. If it's going too slow, you're going to get bored. You might eat a chocolate, do other stuff like that. If it goes too fast, you're not going to be able to grab all those things before they're going off the end of the conveyor belt. I mean, if you're bored, just look up I Love Lucy chocolate conveyor type of thing there. But it's kind of the same idea here. If you increase that filtration rate, it's like turning up the conveyor belt. You're going to get more chocolates, and it's going to be harder to get those in the box. And again, you get too much speed on this one, we start having stuff end up in the urine that shouldn't. And the opposite's also true. If it goes too slow, you start reabsorbing waste products that you don't want to be reabsorbing. So we need the sweet spot in terms of filtration rate for the kidneys to do their job most efficiently. Too much filtration rate, too high of a filtration rate, too low of a filtration rate, both are going to cause problems in the long term. And again, highly regulated by the kidney on this one. This is part of the reason the kidney is so intermingled in blood pressure regulation, because we need hydrostatic pressure and we need it to be in a certain spot for the kidney to be able to do its job. And again, kidneys are really regulating how much urine they're making based on your hydration status. If you're drinking more, you're probably going to make more urine. And we can do a lot of this by influencing those afferent and efferent arterioles, messing with those filtration membranes. When we talk about factors that can influence filtration rate, we talk about intrinsic and extrinsic controls. Intrinsic controls are things the kidney in and of itself it can do without affecting other systemic stuff. Extrinsic controls are the kidney influencing stuff outside of the kidney in order to bring pressure into the range what we want it. So these intrinsic controls, there's really a couple of them here. We have what is called the myogenic mechanism and the tubular glomerular feedback mechanism. And these, if your systemic blood pressure is within a certain range, these are what really the kidney is going to work with on these ones. So the myogenic mechanism involves contraction of smooth muscle in the afferent arterial, so the one bringing blood into the glomerulus. So like it says here, if you have decreased blood pressure, there's less stretch in the smooth muscle that arterial. And these are kind of counterintuitive because of the fact that if we're not getting a lot of pressure in the glomerulus, what we're going to do is we're actually going to dilate the blood vessel going into the glomerulus so we can get more blood into the glomerulus and build up pressure there and choke its exit. So in the case here, decreased blood pressure, you have less stretch on the smooth muscle of the arterial going in. It actually causes its walls to relax and vasodilate, which lets more blood get into the glomerulus, and again is going to build up pressure in that glomerulus because we're getting more blood in and same amount out, so it's going to build up pressure there, and we can bring up the glomerular filtration rate that way. Again, it's kind of counterintuitive because we're dilating something to increase pressure, but you're increasing the pressure downstream of where you're dilating it. Increased arterial pressure, we get more stretch on this one. This causes that to actually contract. So systemic pressure is coming in a little bit high. We actually constrict the blood vessel taking stuff into the glomerulus, which is going to mean less blood getting in the glomerulus, same amount getting out. It means we're not going to build up as much pressure there, and we can compensate for that higher systemic pressure. Again, keeping that glomerular filtration rate in the sweet spot. So the tubular glomerular feedback mechanism, like it says there, is the backup to this. What we're going to see, and this is part of the reason the distal convoluted tubule we'll see actually loops up right in between the afferent and efferent arterial. One of the things going on with these cells, these are called the juxtaglomerular cells or apparatus. If glomerular blood pressure is high, it means we start pushing more salt into the urine. And this can be detected by those juxtaglomerular cells where this loops back in between the afferent and efferent arterioles. If we start seeing that there's more and more salt ending up in this, what happens is these juxtaglomerular cells are going to trigger further vasoconstriction of that afferent arterioles to tone down the pressure. And it's really the combination of that myogenic mechanism and the tubular glomerular mechanism here. As long as your mean arterial pressure, as long as your systemic pressure, that mean arterial pressure is between 80 and 180 millimeters of mercury, we are going to be okay. Those things can do that. Below that 80 millimeters of mercury, in terms of blood pressure coming in there, what happens at that point you've maxed out the ability of these intrinsic mechanisms to do their job. If that pressure gets too low, at this point you're not going to have enough pressure to generate the filtrate sufficiently, and you're going to stop limiting waste in the urine. Again, you've dilated them all the way you can. And the opposite is true is if you get the blood pressure above 180 on that arterial coming in. At that point, we are choking it off as much as we can. We're constricting it as much as we can, and you're still going to be pushing more fluid through than you want to be doing because the pressure is so much higher. So again, it's that 80 to 180 is that sweet spot for the intrinsic mechanisms to do their job. As long as the systemic pressure is within those ranges, the kidneys can do their job with just the intrinsic control mechanisms. And I think I have a little graph right here. So mean arterial pressure is right here between 80 and 180. Renal autoregulation is sufficient to do this. If it gets beneath that, urine production is going to be insufficient. If it gets above that, it's going to be too much, and that's when we start having the kidneys have to bring in other mechanisms outside of the kidney to help try to deal with this. And that's where we get into those extrinsic controls. So extrinsic controls, like I said, physiologic processes outside of the kidney to try to help regulate this. So we can see decreases with the sympathetic stimulation is going to, if we get increased sympathetic stimulation to the kidneys, we're going to see this can do some stuff here. We can also talk about atrial natriuretic peptide, renin and angiotensin system. These are all things that are part of the extrinsic controls that we can start bringing in when we need to. And we'll take a look at these. Sympathetic stimulation. This is going to, again, if you think about rest and digest, one of the things that's more active during that parasympathetic activity is urine formation. So when you're exercising, your heart rate and honestly your blood pressure, mean arterial pressure is going to be up. One of the things this can do is the sympathetic stimulation can result in a decrease in glomerular pressure through further vasoconstriction to that afferent arterial. Helps to decrease also those contractile cells that are part of the glomerulus, will help constrict those a little bit. Again, this is really increasing output during exercise. Like I said, they're emergency to really kind of reduce blood flow to the glomerulus and save that blood for these stressful conditions for the organs that need it more. So going to get a lot of constriction of both the afferent and efferent arterioles to really try to tone this down with that sympathetic stimulation. Also causes the granular cells of the juxtaglomerular apparatus, those things part of that tubular glomerular apparatus, that they're going to release renin, which gets us to the angiotensin 2, which is going to get some vasoconstriction in certain areas. And again, trying to conserve body fluids for those areas that need it during stress, not lose as much in the urine that way. So we get a decrease with this in urine production. AMP, which we've talked about before, when the heart is getting overstretched, this causes a relaxation along with messing with the sodium reabsorption further down, which we'll talk about. Atrial natriuretic peptide is also going to lead to dilation of the afferent arterial, and it also inhibits the release of renin. So when pressure is getting too high, that it's overstretching the heart, we are going to open up or dilate that afferent arterial and inhibit anything that would increase blood pressure to try to create more urine, increase the glomerular filtration rate, and get rid of that excess fluid so we're not overstretching the heart. And we'll see, we'll also do stuff with water reabsorption with that one, but we'll talk about that later. So this is kind of showing you that sympathetic one here, kind of walking through it nice here. What's going on, sympathetic stimulation of the kidneys, what goes on specifically with the afferent and efferent arterioles, and then how it leads to the contraction of those mesangial cells and reduces the filtration membranes surface area. All these things decrease glomerular filtration rate, are going to decrease urine formation, and therefore increase the availability for other body systems during this stressful time if you're doing your sympathetic stimulation. Kind of the opposite with AMP here. When we're overstretching this, it's going to inhibit renin and angiotensin 2 production, let those mesangial cells relax, really open up and vasodilate the incoming blood flow. All these things are going to increase that GFR, increase urine production, and therefore decrease decrease blood volume. That will actually drop the blood pressure overall, but that's also going to stop the heart from being overstretched. And again, just kind of showing you those filtration membrane again and how we can mess with this afferent. And this shows you that afferent, efferent arterial, and that part of the distal convoluted tubule with the juxtaglomerular apparatus cells in that little area, which I was talking about before, but this is the best picture to kind of show it to you. And again, overall, it's that hydrostatic pressure kind of working against the colloid osmotic pressure and the hydrostatic pressure within the capsule, that generally we want about a 10 millimeter of mercury net filtration pressure of a filtrate being formed. Again, we can modify a lot with these afferent and efferent arterioles through the myogenic tubuloglomerular mechanisms here to try to keep that in that sweet spot. If systemic mean arterial pressures change, we can use that. Again, if it starts getting out of that range that works for us there, we can start using some of those extrinsic mechanisms. And again, this is why the kidneys are so involved with blood pressure regulation. They need that appropriate pressure to make their filtrate, and anything that gets it too far out of whack means you're not going to be filtering your blood correctly. Because of that, the kidneys very tied into blood pressure. And like I said before, it's also one of the long-term ways we can regulate blood pressure is by actually getting rid of that fluid or keeping the fluid in there. Heart rate and vasoconstriction and vasodilation were short-term band-aids where either getting more blood volume or getting less blood volume is the only way to really long-term change the blood pressure a little bit more. And again, showing you these things that we can do here. This is all kind of a review here. AMP versus sympathetic versus the renal autoregulation that we talked about. So what we'll be looking at next here is start getting into those other two processes in terms of what happens with the tubular reabsorption as well as tubular secretion and how that does those last couple of pieces that are going to be involved in urine formation.